So today's lesson is essentially about kinematics, which is basically the study of movement, like position and speed and acceleration. So this is a topic that's going to be hopefully, unsurprisingly, really quickly and readily understood by those of you that have studied some physics, but I'm really going to try and cover this like from the beginning, so that whether you've ever taken physics or whether you've taken tons of it, you'll sort of have a good starting point for the calculus that we're going to do with kinematics. So before we get started, let's go ahead and take a deep breath, and let's begin. So the first couple of sections of this lesson are going to be about like key terms, right? So in the course of the next several lessons, we're going to be talking about terms like displacement, distance traveled, velocity, speed, and acceleration. So the first thing I'm going to do is sort of get into what displacement is and what distance is and sort of what the difference is between the two of them, okay? So displacement is essentially just a measurement of how far you are from some sort of starting point. Okay, so how far displaced you are from a starting point. Okay, so displacement, really just a measurement of how far you are away from some sort of a starting point. Okay, now distance, or specifically distance traveled, is a measurement of the distance that something has traveled, usually during some sort of an interval of time. Now, as we're sitting looking at these here and now, it may seem like displacement and distance traveled are the same thing, but through this next really simple example, I hope to show you that they can be quite different. Okay, so as a very simple example, let's suppose that there's a runner that completes 5 laps around a 300-meter long loop, like kind of like a circle or an oval track. Okay, so question A is asking, okay, what was the runner's total distance traveled during this time? Okay. Well, again, if you imagine that there's sort of this loop that they're following, and they're starting here and they're ending here, they go 300, 600, 900, 1200, 1500. Okay, so we would expect that in part A, they ran 1500 meters. And we also could have figured that out by just doing 5 laps times 300 meters per lap. Okay, not surprising. Now, part B. Part B says, what is the runner's displacement from the beginning of their laps to the end of their laps? Now, I'd encourage you to pause the video and think about that for a second. Like, even if you barely understand these terms, if you understand that total distance traveled is the total distance you traveled, but displacement is just how far you are from where you began, what would the displacement of the runner be? Hopefully you recognize that the displacement is 0 meters, because the start line and the finish line are the same thing. Right? So that doesn't mean that they ran 0. It doesn't mean like, the runner didn't go anywhere. No, it just means that specifically their displacement is 0, because they are not at all displaced from where they began their run. So I hope that simple example sort of gave you a sense of the difference between displacement and distance traveled. We're going to see a little bit more of that difference today, but we'll be making more sense of it sort of tomorrow or in future lessons as we work further through this. So I have an example here that's going to deal specifically with displacement. Okay, so again, there's not going to be any calculus here. This is just about making sure that we understand sort of what these things are representing. So the displacement of a child from their parent is given by this function. P of t is t squared minus 4t plus 1. Okay. By the way, displacement is often, like the letter we often use for it is s, but in this case I decided to use p because parent, what the heck? I mean, that's what I decided to use, but it's common to use s. Okay. And t here would represent time. So question A, find the displacement of the child at times t equals 1 and t equals 5. And the question I'm asking here is, what could these things mean? So computing these things is easy. The interpretation, it's not hard, but it's something we'll need to talk about. So to find the displacement at t equals 1, we'll do p of 1. And when I plug that in, I'm just going to get 1 squared minus 4 times 1 plus 1. That looks like it's 2. And similarly, p of 5 would be 5 squared minus 4 times 5 plus 1, which is 25 minus 20 plus 1. Oops, I just realized up here this should have been negative 2. My mistake. Okay, and then this one down here, it turns out, looks like is positive 6. Now, what could these mean? Like specifically, and the reason that this was important up here is that one of these was negative and the other one was positive. What, and I know the problem doesn't explain it, but what could it mean if the displacement is negative versus positive? Right? Well, I mean, what this very well could mean is that this could be 2 units like behind the parent, whereas this could be 6 units, meters, feet, whatever they are, in front of. Like it's common for negative to represent like behind or, before or below, but I didn't think that we were like displacing a child like down into the ground and then back up. That it just seems like troublesome. So just be aware when you have a position that's negative, it probably means like behind or backward or something like that. Okay. Now part B asks, at what times is the child standing right next to their parent? Now, like mathematically, what would it mean that they're standing right next to them, right? Wouldn't right next to essentially mean that their displacement is 0, right? Because they're not displaced from their parent, right? So when it says at what times is the child standing right next to their parent, we would just need to solve 0 equals t squared minus 4t plus 1. This isn't factorable, so you could either do this by completing the square or by the quadratic formula. I know how a lot of you feel about the quadratic formula, so maybe we'll look at completing the square really quickly here. For completing the square, we're supposed to do half of this term and square it, right? So there's this idea that we need a plus 4. So it essentially means that I'm going to add 4 to both sides of this equation so that I can get it to be a sort of a completed square form. This will give me 4 equals t squared minus 4t plus 4 plus the 1 that was already there. I'll subtract the 1 over. 3 equals t squared minus 4t plus 4. Now the reason that completing the square is called completing the square is that we've completed the square over here. Haha. This is now t minus 2 squared. See how we've completed it? And then from here we could square root these things. So when I square root both sides, I get plus or minus root 3 equals t minus 2. And so it looks like the times are 2 plus or minus the square root of 3. Those are the 2 times that this could have happened. Okay. Now, some of you may be wondering, like, is it possible to have negative times? Turns out it doesn't matter here because the square root of 3 is actually smaller than 2. But yeah, we can have a negative time that just means sort of before time 0, before the time that we were sort of marking as our 0 time. We'll be dealing with that more and talking about more of these things as we go, but this was just sort of like hopefully a simple example of us looking at a displacement function and what it could mean and how we might use it. Okay, so at this point I want us to sort of take the idea of displacement or distance and just sort of set that to the side for the moment. In this lesson I'm going to be bouncing between a few different things because we're really doing a lot of introduction. So we're going to set aside displacement and distance for a moment, and we're going to move, because it's velocity, speed, it's about movement, we're going to move on and talk about velocity and speed. And the first thing I want to do is I want to point out that speed and velocity are not the same thing. They're related, but they're not the same thing. So let's look here what the difference is, okay? Speed is simply a measurement of how fast something is going, okay? And speed is always a positive number. And you might wonder, like, oh, but what if I like put my car in reverse and go backwards? I mean, I have like negative speed? No, actually, it doesn't mean that. Speed is literally, like mathematically and as a physical constant, speed is always positive. Okay. Now, velocity, on the other hand, and this is, it can be way more complicated than I'm gonna make it simple because we only need a basic understanding of this here. Velocity is an expression of the rate of change of the displacement of an object with respect to time. Now, you may have noticed that there's some real calculus terms in there, right? And this is not surprising. Like, this isn't a calculus unit for a reason. Rate of change is a calculus thing, and I'm talking about that in just a second. So velocity is an expression for the rate of change of the displacement of an object with respect to time. Okay. Now, given that, velocity can be positive or negative. And actually, in more complicated problems, this is the thing I'm not going to talk about right now because we don't need to scare anybody, and it's literally not in Math HL. Velocity is actually something that's called a vector quantity, and velocity in many three-dimensional and higher dimensional applications, in fact, is a vector quantity. For our purposes, I want us to know and understand the velocity is similar to speed, but different. Velocity can be positive or negative. It's something that's called a vector-valued function, okay? So how are they connected to one another? Like, how are the speed and velocity connected to one another? So the good news for you, the simple news is speed is always the magnitude of the velocity. In other words, if you know what the velocity is, you just take the magnitude of that thing, you take the absolute value of that thing, and you find out what it is. Okay. And so that's why when you put your car in reverse and go backwards at 5 miles an hour, your speed is 5 miles an hour, but your velocity, we might say, is negative 5 miles per hour, because the velocity has, as a vector, has the ability to sort of hold on to that negativeness and express it. Okay. So the good news is all of the kinematics problems in our math course are going to involve things moving in straight lines. Okay. So that means that if the velocity is positive, then the object is moving in one direction, and if the velocity is negative, it's moving in the other direction. Like, that's how we're going to think about it. So if you like throw a ball up in the air, velocity positive means it's going up, velocity negative means it's going down. If you've got like an object that's moving along the x-axis, cool, then positive velocity probably means it's moving to the right, like in a positive direction, and negative velocity means it's moving to the left, in a negative direction. Okay. So I want to look at a simple example here, and I forced it to be simple, right? Because I'm going to have this thing moving in a straight line. So this example, the velocity of a squirrel running back and forth from its tree. Let's just pretend for a minute that a squirrel would run back and forth in a straight line and not in some kind of like crazy wild pattern. Although actually, I suppose if you weren't bothering them, I imagine they'd be fairly efficient. But anyway, the squirrel's running back and forth from its tree, right? And the velocity that it's moving at is given by this sine function. Again, we're going to pretend that this is a squirrel with like an advanced knowledge of mathematics, and that it's moving with speed according to a sine curve. Part A. If I asked you to find the velocity of the squirrel when time was pi over 4 and when time was 3 pi over 4, how would you find those things? Hopefully you're recognizing that this is fairly easy. To find the velocity at time pi over 4, I'm just going to plug in pi over 4. That would be the sine of pi over 4 minus pi over 2. That's the sine of negative pi over 4. And if you think about your unit circle for a moment, that's negative square root of 2 over 2. Okay, great. So the squirrel has negative velocity at this time. Right? So that means that the thing is probably moving like backward. Maybe that means it's running back toward its tree. Okay. What about at 3 pi over 4? Okay. At 3 pi over 4, we would have the sine of 3 pi over 4 minus pi over 2, which would be the sine of positive pi over 4. And that we know is positive square root of 2. Okay. Now part B, and I may have already sort of given this one away a little bit, but I want you to check and make sure that you understand it on your own. So is the squirrel moving in the same direction at these two times? And the answer is no, right? No, it's not moving in the same direction, because for one of them, the velocity was negative, and in the other one, the velocity was positive. And we know that when velocity is positive versus negative, those things are moving in different directions. Okay. Now part C, is the squirrel moving at the same speed in both of those times? The answer here is yes, right? Because the speed in the first one is the absolute value of negative root 2 over 2, which is root 2 over 2. And the speed at the second time is the absolute value of root 2 over 2, which is, of course, root 2 over 2. So for as much as their velocities are different, their speeds are the same. Okay, so I hope that the difference between velocity and speed is something that makes at least a little bit of sense to you. Speed is just a measurement of how fast something is going, whereas velocity has a direction to it, and more than that, it's a rate of change. And we're going to be getting into that being a rate of change and calculus and all of that in just a moment. Okay, now here we are. We finally get to the calculus part. Let's look at the connection between velocity and displacement. Okay, so I'm expressing this as a key point here. Okay. If the displacement of an object from a starting point is given by s of t, then the velocity of the object, which is often called v of t, is given by the derivative. Okay, so if you want the velocity, you take the derivative of displacement. If you want the velocity, you take the derivative of displacement. Okay? And it makes sense. We just learned that velocity is the rate of change of displacement. It's how fast your displacement is changing, how fast your distance away from something is changing. That's literally what velocity and what speed are. Okay? So long story short, if you want to find the velocity of an object, you take its displacement and take the derivative. Okay? So let's look at a simple example here. The height of a rock launched upward from a slingshot may be not a great idea, or at least be watching so you don't hit yourself or someone else. So the height of a rock launched upward is given by this function, okay? And so what I want to point out here is, even if you launched the rock like this, and that's not in a straight line, the height of the thing is still measured as sort of like a vertical thing. This is like a one-dimensional movement or calculation type thing. Okay, so I want us in part A to find the height, velocity, and speed of the rock when t equals 4. Okay, so to find the height, to find h of 4, all I need to do is plug 4 into that thing, right? So quick calculator thing here. It's not hard, but it's something that we can save a few seconds by doing on the calculator. When I plug this all in, I find that the height is 128. I didn't give units on this one. Maybe it's because I was afraid to think about either feet or meters, either one of these a dangerous distance to drop a rock from. So I've got the height of the rock here at time 4. How would I find the velocity? Right? How would I find the velocity? Well, to find the velocity, I first need to find the velocity function, right? How would I find the velocity function? Well, I find the velocity function by just doing the derivative of my height function, doing the derivative of the displacement function. So when I do this derivative, I'm going to get, let's see, if I do the derivative of this thing, it'll be 96 minus 32t. Okay? And so now when I do v of 4, I'm going to get 96 minus 32 times 4. And that's 128. So when I do v of 4 is 96 minus 128. This is going to be negative 32. Okay? So more than likely, what does this negative velocity mean? More than likely, it means that the rock is falling back down at this point. Now, last question, what is the speed of the rock at time 4? Right? Do we get that the speed of the rock is positive 32? Hopefully you got that, because all we're doing is we're doing the absolute value of the velocity. Okay? So now, part B. Right? At what time is the velocity of the rock equal to 0? At what time is the velocity of the rock equal to 0? Well, in order to solve that, fortunately, I have a velocity function right here. I could find when the velocity is 0 by setting my velocity function equal to 0. Some of you may notice right there that this is something we've done before. This may sound familiar. In fact, if this does sound familiar, pause for a moment and think about that, because we're gonna get to that in just a second. When I solve for this thing, I'll get 32t equals 96. That means t is going to be 3. Okay. Now, what is significant about this time? Think about this rock. Like, you're on the ground and you've got your like slingshot over here, which is not just a person standing up. Anyway, and you fire this rock up in the air, and so the thing's got like velocity, 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 velocity. And then at some point, it doesn't have velocity anymore, right? At what point is the thing not having height velocity? Isn't that when it gets to the top? And then it starts to have negative velocity as it comes back down? So what happened up here when the velocity was 0? Isn't the significance of this time that it's when the rock achieved maximum height? Okay, so now that we've got that, now that we have that understanding, part C asks to find the maximum height achieved by the rock. I can take this time and plug it back into my height function to see what I get. When I do h of 3 and do 96 times 3 minus 16 times 3 squared, 96 times 3 minus 16 times 9. Whoops, that was supposed to be a times 9. I got this to be 144. So this is sort of the maximum height of the rock. So man, this 128 wasn't even the maximum height. This rock was all the way up to 144 and then coming back down. So unless that was like inches or centimeters, we may need to watch out for falling rocks. So hopefully that made sense, like the way that we can get these functions to interact with one another or work with one another. All right, so I have sort of one more like vocabulary term or like new idea that we need to bring in, and that's of acceleration. Okay. Now, acceleration is an expression of how the velocity of an object is changing. Okay. Now, as a key point, if I wanted to be really precise with you about what acceleration means, the acceleration of an object is, surprise, here comes calculus terminology, the rate of change of its velocity with respect to time. Okay. So expressed mathematically, right, if the acceleration of an object is a of t and the velocity is v of t, the derivative of velocity will be acceleration. The derivative of velocity will be acceleration. So similar to what we saw before, where the derivative of position is velocity, we now know that the derivative of velocity is acceleration. Okay? So this is how calculus is going to come along and meet us in this idea of kinematics. Okay? Now, a really, really important point about speeding up and slowing down. Okay? Because sometimes when we hear the word acceleration, it feels like speeding up. And I want to point out to you that just like velocity can be positive or negative, acceleration can also be positive or negative. But, and this is really important, just because an object's acceleration is positive does not mean that the object is speeding up. Okay? I want to be very, very clear about this. Okay? An object is speeding up if its velocity and acceleration have the same sign. Okay? So if velocity is positive and acceleration is positive, then it is speeding up. It's speeding up like forward, right? But can't something also be speeding up going backward? Sure. If you had something that had negative velocity and it had negative acceleration also, it basically means you're going backward, and the backwardness that you're going, that's even accelerating. You are accelerating negatively, right? Your velocities are changing negatively, which means you're speeding up going backward. So if they're both negative, you are speeding up backward. Okay? Now, on the other hand, if the velocity and acceleration have different signs, then the object is slowing down. Okay? So for instance, if the velocity is greater than 0, velocity is positive, but the acceleration is smaller than 0, it means that you're going forward. Why am I going forward? I'm going forward because my velocity is positive, but I'm slowing down. Okay? And similarly, if my velocity is negative, that means I'm going backward, right? If my velocity is negative, but my acceleration is positive, that means, sure, I'm going backward, but I'm slowing down. Okay? I'm not able to spend more time getting into exactly why that is. If that's something that isn't clear to you, like let me know, and it's something that we can talk about individually. But the key point for here is objects are speeding up when their velocity and acceleration have the same sign. They're slowing down when the velocity and acceleration have different signs, sort of when they're fighting against one another. So now I want to sort of get into an example of where we might see acceleration come up in a problem. Okay, so suppose that the position of an object moving along the x-axis, so imagine you've got like an x-axis here, and there's something that's moving along the x-axis, moving left and right on the x-axis. It's given by this function, okay, where t is time. Part A is asking us, okay, could we find functions for the velocity and acceleration of the object? Well, sure we could. Wouldn't velocity, how would we find velocity? Wouldn't it be the derivative of that position function? So if I just do the derivative of this thing, I'm going to get, well, the 24 is going to turn into 0. This would be minus 4t plus 3t squared. Okay. Now, similarly, could I find the acceleration? Sure. The acceleration would just be the derivative of that velocity function that we just found. Or if you're sort of paying attention to your notations here, this could be the second derivative of your position function. Okay? So hopefully now it's making a little bit of sense of why we've talked about derivatives, about second derivatives. Those things have application, and kinematics is one of the really solid applications. So for this one, I just need to do another derivative. This would be negative 4 plus 6t. Okay? Now, question B. Determine if the object is speeding up or slowing down at time 1, and part C is actually going to be the same question, just at time 2. So I'd encourage you to pause the video, think about what I mentioned in the previous slide, and sort of put it into application here. So to determine if it's speeding up or slowing down, I need to compute what the velocity at 1 is and what the acceleration at 1 is, and then I need to compare them. So when I plug 1 into my velocity function right here, I'll have negative 4 plus 3, that's negative 1. At this point, can I tell if it's speeding up or slowing down? Nope. All I can tell is that the thing's moving left, right? It's moving in the negative direction on the x-axis. Now what about a of 1? A of 1, I'd use this, the acceleration function. This would be negative 4 plus 6, which is 2, right? So even though the thing is going backward, its acceleration is trying to pull it this way, which means the thing is slowing down. As it's going backward, it's trying to go more positively in its speed, It's changing positively, so it's slowing down. Slowing down at t equals 1. Okay. Now, what about the acceleration? What about, what about the other one? So that was part B. Part C, so what about v of 2? If we do the same problem, again, I come back up here, negative 4 times 2 plus 3 times 2 squared. That's negative 8 plus 12, so my velocity here is 4. My acceleration at time 2, again, I come up to this function again, negative 4 plus 6 times 2, that's negative 4 plus 12, which is positive 8. What do we notice here? Hopefully notice these are both positive, so this is speeding up. Speeding up at time 2. Okay, and then my last part here, right? Use the position and motion of the object at time 1. Describe the position and motion of the object at time 1. So I want to describe it, right? And your description should use words and phrases like where it is, whether it's moving toward or away from the origin, and whether it's speeding up or slowing down, right? So there is one other piece of information here. There's one thing you'll need to calculate, and then I'll want you to think about and sort of write this statement. So pause the video, take a moment, and try that out. So for part D, the first thing I need to do is I need to compute where it is. What is x of 1? Well, when I plug this in, I'm going to get 24 minus 2 plus 1. That's 23. Okay. And now I'm looking at this thinking, okay, so this means that the object is 23 right of the origin. Now, why did I say right of the origin? Well, because this is positive 23, and when we think about our x-axis, we generally think of positive values to the right. So my object is 23 units to the right of the origin. Now, what about sort of the direction that it's moving, or its speed, right? Well, we knew from up here in part B that its velocity is negative 1. So which way is it moving? If its velocity is negative 1, it's moving toward the origin. Okay, so it's moving, so even though the thing is over here, it's moving back toward the origin, right? We could even say toward the origin at a speed of 1. Okay, moving at a speed of 1, because the velocity is negative 1, so the speed is 1, and slowing down. Right, and it's slowing down because we had found up here that the velocity and acceleration are sort of at odds with one another. Now, there's a lot more to learn about kinematics. There's a lot more that we can practice with. Some of you may be noticing that we only did derivatives today, and it makes you wonder if you can do anything with integrals. That's something that we're going to come back to. We're going to get there, but it's going to take some time to move through kinematics. So hopefully this made sense. As always, if you have questions, please let me know. Best of luck as you work through the exercises for this.